Okay, today we're going to delve more into U-substitution than the little kind of preview I gave you yesterday. Last year, some of you were just able to kind of see what you had to undo to make the U-du substitution work. But this year, the problems are going to become more difficult. You're going to have to write out your U and your du. So if you look here, what I'm saying is that when you change to u, your dx has to really be du, and so everything that's represented in the problem has to be in terms of u. So when you have trig functions and it's mixed with another function, generally speaking, you want to let u be the angle if possible. Okay? So in this first problem, the angle would be x cubed. So the du conveniently is 3x squared dx. So 3x squared dx is here, and then my u is here. So this problem really just becomes the integral of the sine of u. And when I integrate sine, whose derivative is sine, it's negative cosine u plus c. So coming back over here, this integral would be negative cosine, and what's my u? X cubed plus c. So that problem becomes very easy as long as I can represent all of the integral in terms of u and du. Okay, when you have fractions, it is helpful if you can let the denominator be the u. And if there's a power on the denominator, you don't typically want to use that power. So for instance, in this second example, I'm going to let u be just that polynomial in the denominator. And when I do that, x cubed plus 3x squared plus 12, my du is then 3x squared plus 6x dx. Okay, so I see my dx here. I see that's my u. But this x squared plus 2x is a little different than what I have here. So let's see. I see a common factor of 3, so if I take that out, I have x squared plus 2x dx. So when I rewrite my integral, if I write du on top, that's all of this, plus this 3. Well, I don't want the 3 there, so I put a 1/3 on the bottom. And then on the bottom I have u to the 5th. When I say I put it on the bottom, I put a 1/3 out front, so that 1/3 times the 3 for the du cancel each other out. This integral might be easier to integrate if I rewrite it as u to the negative 5 du. So when I integrate, I add 1 to the exponent, so that would be negative 4, and divide by the new exponent. So I'd have 1/3 times u to the negative 4 over negative 4 plus c. So coming back to my original problem, this integral would be negative 1/12 because of this, and then I would have u to the negative 4. So if you want to put the answer back in the original form it was, I can put it in the denominator. So my u was x cubed plus 3x squared plus 12, and that would be to the 4th, and then plus c. Or I could use it to the negative 4th on top. So it's going to become very important very quickly that you write out your u substitution. I've been trying to get the AB teachers to go ahead and teach it that way, and I think some are, but some are still reluctant to do that. And it does help BC calculus if you write out the u substitution right at the beginning. Okay, a couple more examples here. So we have an E problem, and you might think, well, E is easy because when I integrate E, I get E. That's true, but when you put an exponent that's not just x on it, then it becomes a little bit different. So typically you want to let u be the entire exponent, So u is going to be negative 9t. Don't just use positive 9t because then that just gets confusing. So my du is negative 9 dt. So I see that I have an extra negative 9. I have a dt, but I have an extra negative 9. So that means in my integral I need a negative 1/9 e to the u du. So this now represents this. And so when I integrate e to the u, I get e to the u plus c, but I have this negative 1/9 out front that has to go along for the ride. So that means the answer to my integral would be negative 1/9 e to the negative 9t plus c. Okay? All right, so you might think, oh, integral tangent. Well, why do I need a u substitution in that? Well, do we have a derivative, do we have a function whose derivative is tangent? We don't. So we're going to have to use some trig identities to rewrite our tangent to begin with. So how can we rewrite tangent? Well, the easiest way is sine over cosine. Now, if you remember back to example 2, I said typically when we have a fraction, we want to let the denominator be u. Because when you do a derivative of just a regular polynomial or a regular function, the derivative is going to go on top. So that's why I want the u to be whatever's on the bottom. So in this particular problem, I want the u to be cosine theta. And then whose derivative, when I take the derivative of cosine, I get negative sine theta d theta. So when I write my integral, I know I have u to the negative 1 because it's on the bottom, and when I put my du, I get all of this, but I have an extra negative. That means I throw a negative out front. Now remember, when you integrate u to the negative 1, if you add 1 to negative 1, you get 0. You can't divide by the new exponent of 0. So that means there's a special rule for that particular integral, and that is it's a natural log. So it's negative natural log absolute value of u plus c. So oftentimes students will forget the absolute value. Please remember that it's negative natural log absolute value of u. So if I come back over here, I will then say that the answer is negative natural log absolute value. Remember, u was cosine theta. Oops. Absolute value plus c. Now, if you look at your integrals that you have to learn, you'll notice that this is one of the integrals you have to learn. And it has another form, and the other form is the natural log of the absolute value of secant theta plus c. I think this one's easy to remember. The reason that you can change those is because, remember, this negative can become an exponent. So if I put it on an exponent on cosine, that's really the reciprocal of cosine, which becomes secant. So we kind of just proved what the integral of tangent was. So you may now memorize that and not have to use a u substitution. Okay? Hopefully this makes sense. All right, so radicals can be like fractions in that you let u be what's inside the radical, because if I let it be the radical itself, I would have a chain rule issue that I would have to then have another radical for a derivative, and that's not going to work because I only have this piece here or this piece here in number 6. Okay? So, all right, so typically I'm going to let u be whatever's inside that radical. So inside that radical is 5x plus 1. So that means my du is 5 dx. Okay, well, we have a little bit of a problem. And the problem is that the du does not have an x in it like the x is here. We're going to learn some other ways as to how to work this problem, I think. But the easiest way to work this problem is to then solve for x in terms of u. So hopefully it makes sense that I cannot write this integral, because if I did this integral as u to the 1/2 du, I'd have an extra 5, so I do 1/5, but I'm missing my x. So that does not work. So I'm going to look at my u and I'm going to solve for x. So I'd subtract 1 and divide by 5. That would be my x. So my new integral then would be, okay, x, which is this, u minus 1 over 5, times the square root of 5x plus 1, which I let that be u, and then dx, which is, du, which is 5 dx, and I have to get rid of this 5 because I don't have a 5 in the problem, which means I need a 1/5. Now, you may say, well, that doesn't look much easier, Ms. Merchant. Well, there was no other way to integrate what I had there. So let's clean this up with some algebra. Okay, I can bring this 5 out here with this, so that becomes 1 over 25 times the integral of u minus 1, oops, I'm sorry, that should have been u to the 1/2 because it's a square root, right, du. In which case then, I can still do some algebra. I can distribute this u to the 1/2. So I'd have 1 over 25 times the integral of, so when I multiply variables with the same base, I add the exponent. So that exponent is 1. 1 plus 1/2 is 3/2. And 1/2, so that's just u to the 1/2. All of that du. Now I'm able to integrate that particular problem. Okay, so I add 1 to the exponent. So 1 and 3/2 is 5/2. So that's going to be 2/5 u to the 5/2 minus 1/2 plus 1 is 3/2. So 2/3 u to the 3/2 plus c. Kind of messy. But then my answer to this particular problem up here, if I distribute the 1/25, I'd have 2 over 125. 5/2 is really the square root of u, 5x plus 1, to the 5th power, minus 1/25 times 2/3, so that's negative 2/75 times the square root of 5x plus 1 cubed plus c. So that would be the answer to that problem. Tougher, much tougher than what you're used to seeing. So I go back to a little bit of an easier one. Now, I don't have a whole lot of room to write this one, so I'm going to go to the next page and rewrite this problem so we can work it out. I'm going to leave space for 7, so I'm going to come back down here to 6. So 6 was a definite integral from 0 to 2 of x squared times the square root of x cubed plus 1 dx. So again, we said, all right, if I have a radical, I want the u to usually be what's inside the radical. So if u is x cubed plus 1, then my du would be 3x squared dx. And that is nice because the only thing that's extra is that 3. So I have to undo that with a 1/3 out front. And then my problem becomes, here's my du, and so I'd have u to the 1/2 du. Now you'll notice that I am not changing my limits of integration over here. I don't want to do them in terms of u. The AP test will force us sometimes to do that, but we are not going to. Oftentimes it is easier not to. It is easier just to do the U-substitution over here and then plug in the original problem. We'll talk about when it's easier not to do that. But at this point, I'm not going to change my limits of integration. I'm going to just use my U-substitution for integrating. So u to the 1/2, when I integrate that, that's going to become 3/2. So it's going to be 1/3 times 2/3 u to the 3/2. And then I will put a plus c because my particular integral was not a definite integral. So when I come back to my original problem, I'd have 2/9 times, let's see, u to the 3/2, which means square root of u was x cubed plus 1 squared, and then I don't want a plus c, I'm going to evaluate that from 0 to 2. So I have 2/9 times the square root of 2 cubed plus 1 is 9 squared, plus, minus 2/9 times the square root of 1 squared. Okay, so remember from algebra that you can do 9 squared and then do the square root, or you can do the square root of 9 and then square your answer. Power to power, doesn't matter what order you do it in. So I'm going to do the square root of 9. The square root of 9 is 3. 3 squared is 9. Minus 2/9 times the square root of 1 squared, which is just 2/9. So, hang on. I made a little mistake here because 3/2 power is the square root cubed. So this should actually be cubed. Sorry about that. That should actually be cubed. So the square root of 9 is 3. 3 cubed is 27. This still says 2/9. So let's see. 9 goes into 20. So that's really, hang on, so that's really, I could really say that's 2/9 times 27 minus 1, if I factor out the 2/9, which was probably easier, which is 2/9 times 26, or 54/9. Nope, 52/9. Hopefully I didn't make too many mistakes and lost you there. Okay, I think there is a way for me to edit these videos, but it's a new option and I will need to figure that out. Okay, last example. So, when you're doing trig functions, and this will actually become a whole section of itself when we're doing U-sub, we'll call it integrating trig functions, but when you have powers of trig functions, you want to look at the smallest power, generally. So my smallest power is that. Is that a derivative of something? Well, yes, that's a derivative of tangent. So if u is tangent theta, then the derivative of u would be secant squared theta d theta. So this is all du. That just means I have to put a power on my u for my u substitution. So this would be the integral of u to the third du. Remember, there's my du. My du's here. Here's u cubed. Again, I'm not changing my limits of integration. So I integrate. That's an easy integral. So that's u to the 4th over 4 plus c. So coming back to my original problem, u is tangent, so that becomes tangent to the 4th theta, evaluated from 0 to pi over 4. Hopefully you remember all of the trig that you learned in pre-calculus. I know you didn't use a whole lot of it in AB calculus, but hopefully you will remember some of it. So when I plug in pi over 4, I'd have tangent pi over 4. Really, that means to the 4th power over 4 minus tangent 0 to the 4th power over 4. The tangent of pi over 4 is 1, and 1 to the 4th is 1, so that's 1/4. The tangent of 0, 0. 0 over 4 is 0, so my answer is just 1/4. All right, if you have any questions, please make sure you highlight your questions, and we will practice this particular concept of U substitution in class next period.